Okay, so let's try to understand how what we just learned about with respect to the sign of the eigenvalue, how that applies to an actual system. So let's look at, for example, very concretely, let's look at x prime equals 1102 times x. Now, I know you know how to solve this. What you're going to do is find the eigenvalues, associated eigenvectors, and assemble them in your ansatz in a superposition, right? So I'll spare you the details of the calculation and go ahead and tell you that we have v1, an eigenvector given by 1, 0, with eigenvalue lambda 1 equals, what is it? I believe the eigenvalue for this one is 1. Okay? And v2 is going to be the eigenvector 1, 1. And this will have eigenvalue lambda 2 equal to 2. So those are my two eigenvectors. And what I want you to observe with your eyeballs is that these are positive and real, both of them. So if I go to plot this system, the vector field of the system, I'm going to do my best. Okay, the idea is that I'm going to have a pair of eigenvectors, one pointing in the 1, 0 direction, which is along the horizontal axis, the x1 axis, and then one in the 1, 1 direction, maybe something like this. Yeah? Each of these determine a line. Wait, maybe I should do them in red. Here's one in red, and here's another in green. Each of these determine a line, like this. Okay? And along this line, because these eigenvalues are positive and real, the vector field in blue points away from the origin. Like this and like this along the red thing. Okay? It turns out like you can get a pretty good sense for what the vector field looks like away from these two lines as well. They're going to sort of asymptotically get closer and closer. They kind of point toward these eigenvectors in some sense. Now, we call this point. I want you to notice we have this special point here at the origin. Have you ever noticed, and maybe this is true generally, or not maybe, have you ever noticed that when you have a system like this, x prime equals p times x, that x equal to 0 is always itself a solution. X equal to 0, 0 is a solution. In other words, x equal to 0, 0 is what we call an equilibrium solution, because it never moves away from x equals 0 from that point. It's a stationary point. If you are a particle and you're being buffeted by the wind and you're sitting right here and the wind is being described by this vector field, okay? You're just going to stay there, okay? You're just sitting there, right? And you never move. All right. So we call x equal to 0, 0 sometimes an equilibrium or a node. An equilibrium or node solution. So it's a solution, okay? But the feeling I want you to feel is that if I was to perturb a little bit away from x equal to 0, then I would zoom very, very far away from x equal to 0. It is an unstable equilibrium, however. In this case, it is unstable. Because if I perturb a little bit away from 0, then I zoom very, very far away from 0 with time. I go further and further away with 0 from 0 with time. Okay. We also call 0 in this case a source. It's a source, not a source. It's a source, okay? Because if you think about it in terms of like fluids, it's kind of like the fluid is receding away from this fountain. Like there's this fountain at 0, which is spewing out water, and the water is receding away. The packets of water are all kind of moving away from the source. That's why we call it a source. Let's contrast that with the... Oh, and by the way, this is not a great picture. Let me show you a better picture. So let me erase this. Delete. And let me paste something. Do I have it pasted? I don't. Okay, so let me grab it from, not here, but from here. This one. This is a much better picture. Copy image. Paste it. Allow paste. Here it is. This is a picture of the same system, but a much better one. You can see here 1 1 1 0, the line determined by it. Okay, and you can see here the line determined by 1 1. And hopefully you can see what I mean. That when we are at x equal to 0, okay, we recede away from it. If we perturb ourselves just a little bit from x equal to 0, if we get a little bit off of x equal to 0, then we're going to recede away from it. We're never going to sink back in, okay? That's why we call it a source. Okay, let's contrast that with another case. This is when x prime is going to be negative 1, negative 1, 0, 2, negative 2. So in other words, I just negate all of the entries of my matrix. Then it's going to turn out that our eigenvectors, our eigenpairs, are going to be negative 1, 0 with lambda 1 equal to negative 1. Oh, no, I'm sorry. It's going to be the same eigenvectors. My bad. Same signs on the eigenvectors. But the eigenvalues will have flipped. Okay? And V2 will be 1, 1 with lambda 2 equals negative 2. I mean, if I did negate the signs on V1 and V2, that's not a big deal or anything, because we know for any eigenvector, a scalar multiple of it is also an eigenvector. Okay? I won't belabor this point. I'll just show you the picture, because I think the picture is in here. Where is it? Here it is. Let me copy this guy. Copy and paste. Allow paste. And there's the guy. Okay? Now, where's 1, 0? Here is 1, 0. Still along here. Maybe I'll do this in green like I did above in the other picture. There's 1, 0. And you can see now the vector field points in along this guy here. And where is 1, 1? It's right here. And now we can see that the vector field also points in. Shoot. In toward the origin. And so this equilibrium point is not a source, right? Because all of the arrows seem attracted to it. We call, in this case, x equal to 0 a sink. It's a stable equilibrium. If we perturb a little bit away from it, if we perturb a little ways away from it, it'll be attracted to go back. Okay? Stable equilibrium, also known as a sink. There's one more case that I want to talk about before the end of this video, and that's a saddle. And let me just show you an example of that. Here's a saddle. Paste. Allow paste. There we go. Here's a saddle vector field. The equilibrium here, x equal to 0, is a saddle point. Because in one direction we have that attractive behavior, and in the other direction we have this repulsive behavior. So the two eigenvectors are going to determine two lines, this one and then this one in this picture. And again, in one direction we have the repulsive behavior, like this, and in the other direction we have the attractive behavior. We call such points with this sort of split personality, we call them saddle points. Okay, and an example of a system which exhibits this would be something like x prime equals, in fact, the picture that this is of is 1, 1, 0, negative 2. And you can see we have one positive eigenvalue, 1, and one negative eigenvalue, namely negative 2. Okay? All right. So this is the saddle. So we now understand sources, sinks, and saddles for our equilibrium solutions. Okay? Next video, we're going to look at the complex case when we have complex eigenvalues, because that's going to be more, imagine this, complicated. Okay, see ya.